If we know how to represent whole things using whole numbers in mathematics, how do we represent something that has been broken down into smaller portions or parts of the whole? A mathematical system that allows for fractional quantities, as they're called, is more complete than one that does not. There's lots of good videos and pictures and things like that to describe fractions and learning about them, why we use them. Let's look at kind of a basic understanding of what is a whole and what are some parts of it. So let's say I have a piece of lumber here. Now, let's say I wanted to split this up into a half. So what I could do is I could take the exact same piece of lumber, see if I can make it the same size. Yep. And I could split it right like this. I could go right here. Now I also could take this thing and instead I can split it like right here. Now, which one would you say is a half of this? This is our whole board. This is our whole. Now, which one do you say is half? Hopefully you said the top one. And that would be correct, because the top one kind of executes this knowledge of precision in mathematics, whereas there's only one way to have two equal portions, right? These two sides here look almost equal, and if they're not equal, that's because I drew it wrong. But imagine that they are equal portions. There's only one way to draw this equally along this line here. This black portion here is definitely not the same size as this green portion. We have to have the same equal portions to get this precision in mathematics. The bottom, however, it may not be a half, but if we cut it correctly, let's see. Let's say I cut it this way here. They're not exactly equal because my drawing's not very great. But you see here, instead of this being a half that I had previously, which was this little portion here, now this is actually two parts, two parts of 6. So each one of these parts here is 1/6 of the board. And so we had 2 parts of that. Let's follow this idea of these portions here, and let's try and figure out what is a third and what is a fourth. Well, a third is going to be 3 equal portions, and that looks to be like that. Each one of these portions are about the same. And a fourth, well, if we cut it in half and then cut each of those halves into half, now we have fourths of this board. And you'll notice that each one of these boards are the exact same size as our whole there at the top. That's because we're talking about a half, the sixth, the third, and the fourth. According to this whole board here, this whole is what they're all relative to. And fractions are always going to be relative to some whole. The whole in mathematics needs to be one that's arbitrary so that it can satisfy every situation and every problem that you may come across. And this whole in mathematics is going to be the number 1. The smaller portion of 1 is called a proper fraction. Whereas these ones here that we had, if this is 1, then this one's going to be, there's going to be 2 parts to the whole. This one's going to be 6 parts to the whole. This one's going to be 3 parts and 4 parts to the whole, which is the 1. Now, why am I writing these things down? Because there's things called proper fractions, and a proper fraction has 2 parts. For this second one here, let's say we're looking at just this first part. This is 1/2 of the whole. There's 2 parts, 2 equal parts to represent the whole, and so we say we have 1/2, because the 2 is how many parts represent the whole. The top number here is called the numerator. The bottom number here is called the denominator. And the top tells you how many parts of the whole we're talking about, and the bottom number tells you how many parts make up the whole. Okay? So for this next one, right, we said there's 6 parts to this whole, and you can see there's 1 here, 2 parts that we have. We have 2 parts out of the 6 total parts. The next one we have, if we were looking at this one, this would be 1 part out of the 3 parts that make the whole piece of lumber. Last one here, let's look at this here. This is going to be 3 parts out of the 4 parts that make up the whole piece of lumber. All of these are called proper fractions, because the numerator, the top number, is less than the denominator, the bottom number, which is the whole portion. So as I said, these are called proper fractions. Now there are 3 types of fractions. The first one is proper, which we just talked about. That's where the numerator is less than the denominator. Improper fractions are where we are discussing more than the whole. So that's where the numerator is greater than the denominator. So for instance, let's take the 3 here. Let me draw this out here. Let's say we had a piece of lumber. This is our piece of lumber. I'm going to cut it into thirds. And then in addition to this, we had another piece of lumber. Okay? The question is, how many pieces of lumber do we have here? Well, we have 1, 2, 3, 4 pieces, 4 parts, and each of these parts is a third, or in other words, 3 parts make up a whole. So we have 4 thirds, and this number is going to be greater than 1 because there's more parts than there are that need to make up a whole. And you can see that, right? We have one whole portion here, and we have a little bit more. This is an extra part. And so 4 thirds is the improper fraction that describes this. Now, there's one more type of form of a fraction that we use, and that's called a mixed number. And it's actually the same thing as an improper fraction. We just use it. It's typically used for like application type problems. It helps to read it and to bring it to the real world, make the numbers more real. And so for an for a mixed number, what we're looking here is that this here is 1 whole. So we say it has 1 whole, and you see here, this is 1/3 of a whole. There's 1 part here, and there's 3 parts that make the whole. So there's an additional 1 part of the whole, which is 3. So again, 3 parts make up this whole fraction. We have 1, 2, 3. That's what makes it this whole piece of lumber. And you see we have an additional 1 portion on top of the 3 we already have. So we have more than a whole. So we have 1 whole, That's what this big number 1 here is. And we have 1 part in addition to the 3 wholes. So really, 4/3 is equal to 1 1/3. Okay, since they're equal, is there a way to convert between them? And there is. It's not actually that complicated. One way is just a division. The other way is going to be, we're going to use this algorithm. So let's look at an improper fraction first. 21/4. So think of the lumber. We have, let's say 4 parts make up a whole piece of lumber, and we have 21 parts total. Let's convert this improper fraction into a mixed number. It's quite simple. All we have to do is do the division. How many times does 4 go into 21 evenly? So we can do this multiple ways. You can actually do the division, or you can say 4 times 1 is 4. That's less than 21. 4 times 2 is 8. 4 times 3 is 12. 4 times 4 is 16. 4 times 5 is 20. We're still less than 21. 4 times 6 is 24. So this is times 6. And that's more than 21. So we're gonna go back 1. 4 times 5 is 20, which means 4 can go into 21 5 times, which makes 20. So we go 21 minus 20, and we get 1. And that means there's 1 left over, and we just keep the same denominator, 4. So 5 1/4 equals 21/4. That's because 4 can go into 21 5 times evenly with a remainder of 1. As I said before, you can just actually do the division here. 4 can't go into 2, so it goes into 2 0 times. 4 can go into 21 5 times. 5 times 4 is 20. We get 1 left over, so we have 5 remainder 1. So that's what tells us there's 5 with 1/4. Each of these numbers here, the 5, the 1, and the 4, are all used in the mixed number. Okay, what that means is that if we have 21 parts and where 4 parts make a whole, then that means we can get 5 whole boards out of the 21 parts we had, and we're going to have 1 part left over that doesn't make a whole. Okay, so that's why this mixed number here can be useful for application type problems, because it directly tells us how many wholes we have, and that's typically what we want to know when we're looking at improper fractions. Okay, so this is improper to mixed number. Now, let's go the other way. Let's go mixed number to improper. So there's a simple algorithm that lets us do this. So let's say we have 5 1/4. Well, all we have to do here is take the denominator, 4, and multiply it by the whole number, which is 5. 4 times 5 is 20. And then take that result and add it to the top. So we're going to drop the 5, just get rid of it, because we did 4 times 5 is 20, and then 5 plus 1 is 21. We put that on top, and we just leave the denominator the same, which is 4. And we got back to the improper fraction that we had when we started with. So this algorithm here, take the denominator times by the mixed number, start the whole number out in front, and then add it to the top. We can always use that to get what we need. Let's look at another one here. Let's look at 40/16. So we're going to convert this to a mixed number, and then we're going to convert it back to make sure we did it correctly. So how many times can 16 go into 40? 16 times 1 is 16. 16 times 2 is 32. 16 times 3 is 48. And that's too much, right? So we know there's going to be 2 there. which is 32. 40 minus 32 equals 8. And so we get 8 over the whole, which is 16. So 40 over 16 is the same thing as 2 and 8/16. Let's make sure of this by using the algorithm I just showed you. We take 16, multiply it by 2, and then take 2 and add it to 8. 16 times 2 is 32. 32 plus 8 is 40. And we just leave the denominator at 16. And we get back to our original improper fraction. So that's the correct method there. Let's look at one more. Let's look at, let's see, 3 and 2/3. So what is this as an improper fraction? Well, first, 3 times 3 is 9, plus 2 is 11. Then we, of course, just bring over the 3. That gives us the 3 on the bottom. So we get 11/3. Now, let's make sure we get the same mixed number if we go backwards. How many times can 3 go into 11? Well, 3 times 1 is 3, times 2 is 6, times 3 is 9, times 4 is 12. That's too much, so we go times by 3. So 3 times 3 is 9, so we go 11 minus 9, which is 2. That goes on top, and we just bring the bottom divisor over, and we get 3 and 2/3, which is the original improper fraction, sorry, mixed number we got in the first place. So to recap this procedure, to go from improper to mixed, all we have to do here is divide. Okay, that's the process that I was doing there. To go from mixed to improper, we take the denominator, multiply it by the whole number, and then add this onto the numerator. And we leave the denominator the same. For our next topic, we're going to talk about equivalent fractions. Before we do that, let's look at this circle, which think of it as like a pizza or a cookie or whatever. So we have this pizza, and this is a whole pizza, right? There's no parts missing out of it. Now, if I cut this pizza up into a separate pizza, but just cut it down directly in half. Imagine I'm cutting this directly in half here. Now we have 2 pieces, but we still have one whole pizza because we haven't like eaten any part of it or anything like that. We have 2 pieces that make up this whole pizza. Okay, now let's consider the same thing again. But now instead of just cut it into half, we're going to cut it into fourths. So I'm going to cut it once down, going down, and then once going straight across. Now we have 4 pieces of the whole pizza. We still have a whole, but we have 4 pieces. Now, let's say for the 2 pieces and the 4 pieces, let's say we remove this portion here and these portions here. Okay? So on this first pizza, this black portion is left. It's still there. We have 1 piece out of the 2 that made up the whole pizza. In this portion, we have these 2 pieces still remaining, these 2 black pieces. So we have 2 pieces remaining out of the 4 pieces that made the whole pizza. Now you'll notice that these 2 these two pizzas have the same amount remaining, right? 1/2, therefore, is the same as 2/4. These are called equivalent fractions. They express the same quantity, but they're different numbers. There's a lot of different reasons we use equivalent fractions. Typically, we use it to compare to see if two things are equivalent or not. But this is the idea of what it means to have equivalent fractions. 1/2 is equal to 2/4. I can show you that mathematically by taking 1/2 and multiplying top and bottom by 2. 1 times 2 is 2, and 2 times 2 is 4. And you see we get 2/4. Now, why does this prove they're equal? Well, because if we take 1/2 and multiply it by 2/2, which is the same thing that we're doing there, 2/2, 2 divided by 2 is 1, right? This is the same thing as 1/2 times 1. And we know whenever we multiply by 1, we never change the number. It's called the multiplicative identity. It always keeps the same number, right? 3 times 1 is 3. 18 times 1 is 18. 1 million times 1 is 1 million. It never changes the number. It leaves it the same. And so if we multiply by a version of 1, namely 2/2, we're not changing the number. We're just changing, I guess, like the idea of the number or the version of the number. But it's still the same number. That's why 1/2 is the same as 2/4. Now, 1/2 typically is preferable to 2/4. That's because 1/2 is what's called reduced. We're using the smallest terms. We're dividing out the biggest numbers out of top and bottom. Let me show you how to do that here with a couple problems here. Let's say we had 84/36. So we're looking for a reduced version of this number that's the same number as it, but that uses the smallest terms. And the way we do that is we look at 84 and 36 and ask the question, is there a common divisor? Namely, is there a number that can go into both 84 and 36? And I like to start off with numbers that are small because they're easy to work with. For instance, 2. 2 can go into both of these things. So 84 divided by 2 is 42. 36 divided by 2 is 18. Well, this number can actually be reduced further. We can divide it by 2 again. 42 divided by 2 is 21. And 18 divided by 2 is 9. Now, is there a number that can go into both 21 and 9? And there is. 3 can. 21 divided by 3 is 7. And 9 divided by 3 is 3. Is there a number that can go into both 7 and 3? There is not. 7 and 3 are actually what are called prime numbers, and that means there is no other divisors besides 7 into 7 and 1 into 7, and then 3 into 3 and 1 into 3. You can, of course, divide by 1, but there's no point, right? You can always divide by 1. You always get the exact same number over again. So if 1's the only thing you can divide by, don't do it. It's not going to change the number at all. All right, let's look at another one. 35/30. Let me go back a second. What can divide both 35 and 30? 5 can. If you're not sure, you can always just test some numbers on a calculator. But 5 can go into both of those. 35 divided by 5 is 7, and 30 divided by 5 is 6. Anything can go into both of those? The answer is no. 7's prime, 6 is 2 times 3. There's no common thing there, so that's the best we're going to get there. Now, 28/7, let's reduce this one. What can go into both of those? 7 can. 28 divided by 7 is 4. And 7 divided by 7 is 1. Now, nothing else can be divided here, especially since we have 1 in either the numerator or the denominator. But 4 divided by 1 is 4. We don't really ever say 4 over 1. There's certain cases where we do, but if you're trying to reduce a number, then this is preferable for. Every single thing that I've said here is that 7/3 equals 84 over 36 in reduced terms. 7/6 is the same thing as 35 over 30 in reduced terms. 4 is the same thing as 28 over 7 in reduced terms. And these reduced terms typically are smaller numbers that are easier to work with. That's why we like to do it. Now, the next question is, would we ever go the other way? Would we ever scale up these things then reduce them? And there is cases where we would, and that's typically whenever we want to compare fractions. So let's look at 7 over 8 and 11 over 12. The question is, which one is bigger? Well, these two fractions have different wholes, right? 8 parts in the first one makes a whole, and 12 parts in the second one makes a whole. And you see we have 7 parts for the first and 11 parts for the second. So which one looks better? Well, if you want, we can actually kind of draw these out. I don't know what it did there. Let's draw out 2 bars like this. Okay, let's look at an 8. So I'm going to cut the first one into 8 equal portions, at least somewhat equal. It's going to be hard because I'm doing this by hand. So next one is going to be 12. So let's see, we'll do this. And then okay. So kind of imagine these are equal. 7/8 is this portion here. So we have 7 of these out of the 8. 11/12 is this portion here. And which one is bigger? Well, to my eyes, it looks like the lower one is bigger. So we could say 11/12, but that's not a mathematical proof because this is prone to error. Let's prove it mathematically by getting what are called common denominators. It's like recutting up these boards to where they're the exact same pieces. So what I'm going to ask is, what is the least common denominator between the two denominators we have, 8 and 12? So I'm just going to look at 8 and ask, what are the multiples of 8? 8 times 1 is 8. 8 times 2 is 16. Times 3 is 24. Times 4 is 32. Times 5 is 40. And then it continues. We'll wait to do that. Let's look at 12 now. 12 times 1 is 12. 12 times 2 is 24. And we can stop there because 24 is in both of them. All right. Now, let's make the denominators. Let's scale them up to this common denominator of 24. Well, to reduce, we just divided, right? So to scale up, we're going to do the opposite of division, which is multiplication. 8 times 3 is 24. So 7/8, we're going to multiply on top and bottom by 3, is the same thing as 21 over 24. 12 times 2 is 24, so 11/12 times 2 on top and bottom equals 22 over 24. And now you see that we have the same portions in both of them, 24, and we have parts that we can directly relate. 22 out of 24 is more parts than 21 out of 24. So 11/12 is a bigger fraction out of 24. If you want to see that, all we really have to do is just cut these things further into one into half. All these parts are going to be cut into half. And there's 24 there. And the top one, it was 8 times 3, so we're going to need to cut all of these into 3. Again, this is a lot harder to work with. What you'll notice is that there's the same number of parts into both of these things. We've recut them up. And so now the top one is the same thing as 21, which goes to this bar here. And the bottom one is the same thing as 22, which goes to this portion here. So all we've done by scaling this thing up is change the number of parts that we have. That's with proper fractions. Let's look at one with improper fractions. So which is larger, 3/2 or 13/8? Well, let's look for a common denominator here. 2 and 8, right, are the fractions. 2 times 1 is 2, times 2 is 4, times 3 is 6. Oh, times 4 is 8, which means 2 can go into 8. And of course, 8 times 1 is 8. Oops, 8 times 1 is 8. So 8 is going to be our least common denominator. So I'm going to multiply the bottom and top by 4 because 2 times 4 is 8. On the bottom one here, I can just multiply top and bottom by 1. It doesn't actually change anything. But we get 13 over 8. And now you see directly 13 over 8 is a bigger fraction than 3 over 2. All right, last one. 1 2/5 or 6/4. So here we have a mixed number and an improper fraction. And I will say, working mathematically, it is much easier to work with improper fractions than mixed numbers. So I recommend whenever you do mathematics with mixed numbers, change them first to improper, do everything you need to do, and at the very end, if you need a mixed number back, convert back to mixed numbers. It's going to be much easier to work with improper fractions. Okay, so 5 times 1 is 5, plus 2 is 7. So this is just 7 over 5. And now we can look for a least common denominator between 5 and 4. 5 times 1 is 5, times 2 is 10, 3 is 15. 5 times 4 is 20. Now I will stop there because 5 and 4, 5 times 4 is 20. 4 is the other denominator. Let's just look at 4 real quick. 4 times 1 is 4, times 2 is 8, times 3 is 12, times 4 is 16, and 4 times 5 is 20. And you see 20 is in both of them, so we know 20 is going to be our least common denominator. If you're ever not sure what the least common denominator is, you can always find a common denominator by multiplying the two denominators together. It may not be the least common denominator, but it will get you somewhere that you can work with. So I'm going to multiply 4 by 5 and 5 by 4. Again, make sure you do it in top and bottom. 7 times 4 is 28 over 20, and 6 times 5 is 30 over 20. And now we can directly see that 6/4 has more on the top than 1 2/5 does. If a 12-ounce container of fertilizer is mixed with 48 ounces of water, what is the fraction of fertilizer to final mixture? Now you might be tempted to just go, well, 12 divided by 48, and then reduce that. 12 can go divided by 2. It's going to be 6 over 24. Divided by 2 again. Probably 3 over 12. We can divide by 3 now. It gives us 1 over 4. So it'd be 1/4 of the mixture. But that number would be wrong. That's because the question asks, what is the fraction of fertilizer, which 12 ounces was how much fertilizer was added, to final mixture? What we found here was fertilizer to water. but that's not what the final mixture is. The final mixture is a combination of fertilizer and water. So how much mixture is there when we combine these two quantities together? Well, that would be 12 plus 48, which is 60 ounces. 60 ounces is the amount of mixture that we have. Now, to figure out how much fertilizer is to the final mixture, we take 12 divided by 60. 12 ounces of fertilizer to 60 ounces of the final mixture. And now we reduce. You always want to reduce fractions for a final answer, unless you're trying to do what we did previously, which was to compare fractions. So 12 divided by 2 is 6. 6 divided by 2 is 30. We can divide by 2 again, giving us 3 over 15. Now we can divide by 3, giving us 1/5. And 1/5 is a fraction of fertilizer to final mixture. That answers this problem correctly. All right, a 3/4 inch drill bit is too large, an 11/16 inch bit is too small. What size should we try next? So if a 3/4 is too large, we need to try less than 3/4, but 11/16 is too small, so we need to do more than 11/16. Now, what you'll notice here is, right, we have different size, different holes, right, 4 and 16. So let's try and make one that they're both the same. So let's try and make the same denominator. That's what I'm trying to say here. We can do the whole, what are the multiples of 4? What are the multiples of 16? But if you're keeping your head in the game, as it's called in mathematics, is there a way to make 4 into 16? And there is. 4 times 4 is 16. So we do that, and we get 12 over 16. And now we see directly why 3/4 is too large and 11/16 is too small. 3/4 is 1/16 bigger than 11/16. Now, we need to go less than 12/16, but more than 11/16. And you may say, well, if we do 11.5/16, but this would not be a correct way of writing that. We don't want to have decimals and fractions in there. What we're going to do is we're going to go to the next size up by multiplying top and bottom by 2. Because this way, we get 22 over 32nd. Here we have 24 over 32. So a 3/4 bit is the same thing as a 24 32nd inch bit, and an 11/16 is the same thing as a 22 over 32nd inch bit. Okay? Now we can see, is there a size between these? Yes, there is. Between them is a 23rd over 32 inch bit. That's the size we want to look at. And you can keep expanding this bigger and bigger, right? We could say 51 over 100 and a 52 over 100. Let's say we wanted to get right between the two of them. Well, if you multiply both of them by 2, we get 102 over 100 over 200, and then 104 over 200. Now you can see 103 over 200 is right in the center between them. You can just for any kind of fraction, as long as you can make the denominator bigger, you can always have more wiggle room, kind of is what I think of it as, between the numerators.